AC and HVAC for cells 3 and 4. Today I'll be facilitating this session about the LTT energy. So I hope everyone could attend the past session with my colleague Khaled, where we talked the introduction, the basics of energy, and things like that. For those who did not could attend, hopefully they could see the recorded live session because it's important for some concepts we are going to see here. But anyways, it's not too late. You can always see the session. And also, hopefully, you could work on the case study. We are going to go through the case study all together and see a little bit how did you people went with the case study. So I will now start the session. If anyone has any particular question before we start, please go ahead, just raise the hand and let's hear you. Okay, I assume there are no questions, so
sorry,
let us start.
There is one question from
Okay.
Amidullah.
Yeah, Amidullah.
Yeah, you're mute, Amidullah.
Okay. Hello and good afternoon, dear all. Sorry for this. I have a question about like a few minutes ago, Mikhail mentioned like there is a telecom or ICT training, LTT training in January. And how can we apply for this training? Direct in your email, I will send our application or this thing or what. And if there is a like a LTT in HVAC or this thing, and how can we LTT in how can we apply? And one of our friend in our project, I am HVAC specialized technician, and one of my friend is biomed technician. How can I will inform him for this, like in this week, because we have just in this week, like how can they apply for and how can they register in this LTT biomed? Sorry.
Okay.
Thank you.
Yeah. Okay. For all these questions, Amidullah, if you can wait until the end of the session, then you remind in the session, and then I will answer to all these questions. Like this, we don't interrupt more for this final session of energy, and I will give you all these answers. Thank you.
Okay. Thank you.
Thank you, Amidullah. Is there anyone else, anyone with a particular question regarding the syllabus, regarding what have been said in the last session? Okay, good. So in this final session here, we are going to talk about modules 3 and 4. So power distribution systems and also the electrical safety, protection of equipment and people. Before, of course, talking about our case study. So this is how our session will be. We'll talk about modules 3 and 4, as I said. In case there are any questions, we will talk about these questions, and then we will go to the case study. So first of all, and before we go deep in our subject, is there anyone who can remind us what are the main components of an electrical system? It's something in the syllabus. I hope you guys could go through it. If anyone remembers what are the main components of an electrical system, any of the components. We know there are 4 main components. Anyone?
You can raise your hand or just jump.
Yeah, you
and
can
say.
Yeah, raise your hand or jump. Your mics are muted, just so you can unmute yourself. Okay, so let's move ahead. We were saying that in all electrical system, we have four main components that will make the whole of your electrical system. And these components are your source, could be one or multiple sources, depending on your setup, the distribution system, the protection system, and the user equipment. So the sources, you know, and it was part of the first module, we have power generators or solar modules. That it could also be the grid, batteries, and things like that. So these sources that we use in MSF, they are there to produce the power, to produce the electricity that we need for our activities. Then the distribution system, which are main cables, they are there to carry up this electricity produced by the sources. So the distribution source will carry and distribute the energy, the electricity from the source to the equipments. So they use equipments here, you see at the end. And those user equipments are there to absorb the electricity and use it for the purpose of each equipment. And then apart from that, we have the protection system. So as you all know, the protection system is mainly composed by MCBs, SPDs, AVRs, and all these devices. And they are meant to protect your system. They will protect your cabling, the whole installation, your equipment, and even people. So the users making use of your electrical installation. And they will protect even your sources because, as you know, short circuit could damage the power source. So this protection system are there to protect the whole system. And we have multiple devices we could use to protect your system, as you can see here in the picture. So just to make a bit of detail on this protection system, we will see furthermore. We will see what the purpose of an MCB, of an RCCB. MCB stands for main circuit breaker. The RCCB is the residual current circuit breaker, the surge protection device that we commonly call SPD, then the AVR, automatic voltage regulator, and other devices like UPSs, which stand for uninterruptible power supply. So let's go and move forward if there's no questions about these components of an electrical system. So at any moment, if there's any question, just raise your hands, guy. You can interrupt at any time so we can answer our question to make sure everybody goes aligned with what we are saying and seeing. So as we know, it is essential to have a good electrical installation in place in order to protect people, the equipment, and the installation itself. And all these equipment that are connected to the energy sources, and also to not having power outages, so to ensure continuity in the activities. So all of this relies, first of all, on a very good installation. So a proper implementation is essential. Good quality materials also is needed, and it also passes to qualify the personnel who will be doing all these implementations and following strictly the standards and the guidelines that we have available in our logly. So let's talk a little bit about protection, on how to protect the equipment and the installation, what is needed and how should we proceed to talk about the protection. So first of all, we have here, this is a synoptic diagram of an electrical system. So you have the sources, which in this case you are using the grid. We have the user equipment, and we have the grounding system here and your cabling. So is there something missing in this synoptics illustration, and what is missing? Does anyone knows what is missing here? or the illustration is complete like this. Yes, please go ahead. Just unmute yourself. There's one hand.
Everyone, it's schema. You see there's no any distribution board. So the safe.
I don't know for the others, but I can't hear.
Yeah, we hear you very, very, very far away. I don't know your micro if it's.
Check. That's correct.
Yeah, I think. Right now?
You hear me, sir, right now?
Yeah, perfect.
Yeah.
Clear. Thank you.
Loud
Yes.
and clear.
Yeah, sorry for this.
No problem.
At first, sir, there is no any distribution board seen in this schema. The distribution board has safety breakers like SPDs and also RCD breakers. We didn't see here, and also we need to protect our cold chain from the electrical fluctuations. In here, we didn't see any regulators or AVRs. So that's all. There is no any protection, and also there is no any distribution box. And I think the grounding system is already connected. That's all.
Thank you very much. Thank you very much. Yes, this is the thing. What we are missing here in this particular schema is the protection. So the diagram as you have would work. You would have power in your outlets and in your things, but you would be in a very, very dangerous situation, a risky one. And it's a common error that we may find in some places, electrical protection devices missing. So our colleague mentioned the SPDs, so surge protection devices, RCBs to protect against leakage, and AVRs. So these are three components that we use a lot to protect. Apart from these three, anyone could add any other device that we might be missing for protection. So here, apart from what our colleague just said, and is very correct, we also missing.
I think
We also miss
UPS also.
Yes, UPS, exactly.
Yes, boss.
UPSs. UPSs, we use them for most sensitive equipment to protect the most sensitive equipment, UPSs. Anything else apart from the UPS?
I think one thing more. Sorry that I'm adding one thing more. Voltage limiter, I think, for the electrical water heater protection.
Exactly. Voltage limiter. This one could be used for water heaters, for laptops also. We can use voltage limiters to protect them. And finally, also, and one of the main importance, MCB. We mentioned RCCB, we did not mention MCB. So MCB is also to protect against short circuits and short circuits and overloads. So as you can see here are our protection devices. They should be in our installation in order to make it fully functional and protected and safe. So here we have the MCB that will protect all the installation against short circuits and overcurrents, overloads. We have the RCCB that will protect against leakage of current on the circuit. This is the main MCB, and then we have other MCBs for the circuits. And the SPD, which is not materialized here, but it should be put between the main MCB and all the other devices. We have the SPDs to protect against surges. So these ones will protect the installation, and the RCCB will protect people for safety. And then on the other side, we have these devices here that were mentioned. So we have the AVRs to protect all the devices against voltage fluctuation. We have the voltage limiters, and we have the UPSs. So as you mentioned earlier. So these ones are here to protect the equipment, while these ones are here to protect the installation, the electrical system itself. So now that we are talking about AVRs, let's just remind very quick the difference between a voltage limiter, or how does each of these equipment work and what it does. So first of all, the voltage limiter will just keep monitoring your voltage, because as you know, all your appliances, they are sensitive to voltage fluctuations. And you have voltage fluctuations, especially if you are connected to the grid as your source. And these voltage fluctuations could be harmful for your devices. So the voltage limiter has a specified range, and it will be checking if your voltage goes out of your range, if it's higher or much lower than the range it should allow. And whenever the voltage is out of the range, it will simply disconnect the circuit, so cut the power. This is how voltage limiter works. And then you have the voltage regulators, which whenever the voltage is out of the range, instead of cutting your power, it will try to stabilize the voltage. So it will transform your power and keep it in a steady range. So you have steady values of voltage when you use this one. Then you have the UPSs, which also offers protection against voltage fluctuations, because it converts. It's a double conversion UPSs, which means it will convert your AC voltage into DC to store in the batteries, and then convert again from DC to AC to send to your appliance. This is where we call it double conversion UPSs. And this is the most reliable one because it provides very clean energy. It protects you not only against over voltages, but also against frequency fluctuations. So it will keep your frequency in 50 Hertz exactly, and it will give you some backup. So whenever there's a shortage, the batteries will keep running your system. So these are a bit more expensive, as you can expect, and they are meant to protect very sensitive equipment, the UPSs. Most biomed devices are always recommended to be connected over a UPS. So let's move forward if there are no questions regarding this specific protection material, and see a bit more in depth.
Aurelio, there is a comment on the chat. It says biomed and IT, please. What do you mean, Edgar?
About the UPS sensitive material, like not just biomed, like it could be nice. We are trying to start sending this message, but internet and IT equipment, it's most than recommended to have under the UPS, mainly the routers and the internet antennas, or the telecom, like the radios, like the new ones that are satellite. They are super sensitive.
Edgar, sorry, you can introduce yourself also, because maybe some of the participants don't know. So.
Oh yeah, sorry. Yeah, I'm Edgar Garriga. I'm the ITC referent for the emergency unit, and just now in Darfur. But yeah, like from ITC, we are trying, or we saw that there is a need that taking care, or like taking consideration some materials, some devices, because every day they are more sensible and more delicate. And yeah, I think it could be nice. It's from here we can impose, or we can share the message of protect this ITC material too.
Thanks. Aurelio, you are mute, sorry.
Sorry. Okay. So thank you, Edgar, for your comment and your feedback. Exactly. As Edgar said, this is actually the scenario. This is the case. Most of communication equipment are also sensitive equipment, and they must be protected. Not only because they are sensitive, which means they vary a narrow voltage range that they admit, but also because of the importance and the impact these devices have in the operations and in all the projects we are working on. We know how it could be if we lose communication at any point. So it's very, very important to protect these devices as well. It goes through communication devices, which means all the routers, the Merakis we have there, and even the antennas, like if we have any VSAT, the radios, all this stuff should be also protected by UPSs. So for some of them, in some of the projects, it's also common to see instead of a UPS to have a backup dedicated only for this IT equipment, like an inverter with some batteries, which also offer good protection and much more autonomy compared to the UPSs. Then let's move forward and keep talking about the distribution systems. So when we are protecting this, our power system, we always have, as we saw in the diagram before.
Sorry, Aurelio,
Yes, there's a question.
Yeah.
Yes, just a comment in the previous slide.
Yeah.
Yes, I saw I'm looking something like, yes, about a ground.
Yeah.
The ground system, and I think that is not properly installed here, because the cable, I think that is not the proper one, and the way of installation is not good. Was supposed to be inside of half. Yes, it's just observation in this. Yes, good.
Yeah. Thank you very much for this comment. Could you present yourself just to know the name? So.
Okay. My name is Felisberto Rosario, biomed technician from Akba, Mozambique.
Okay, thank you, Felisberto Rosario.
Yes.
Thank you, Felisberto. So, as you were saying, Felisberto, first of all, the first thing is this thing here shouldn't be exposed. It should be inside a box. We usually put it inside a box to protect the hole. Here, it's open, and we made it expressed open so we can see how the thing is, the connection, the road, and everything, just for illustration purposes. But yes, first of all, we should have a box to protect the thing. So thanks, Felisberto, for the intervention. And after this, the cabling, it will depend on your system and the application itself, where the cable is going to connect, what kind of system it's going to connect. That will define the cable. Here is just a general scenario, we are not talking about a specific scenario, it's a general case. So we have this cable here. For example, if it was an installation where this cable goes for a certain distance before going up to the cutting bar, which means the cable would go buried, then we should put a bore copper cable, the cable without insulation. This is the most suitable, because while your cable go under the ground, you can increase conductivity by leaving this cable non-insulated in contact with the ground. But here, as the cable goes out of the peg directly to the cutting bar without passing in the ground, it's highly recommended to have it insulated, because there's no need to get rid of the insulation if your cable is just going up. It's not in contact with the ground. So this is the second thing. And then the cable section. The cable section, it's advised to have 25 millimeters in the scenario. Here, so you have 25 millimeters going from here to the cutting bar, if it's going to feed a main board, a main installation board. We can have other cases with smaller sections. For example, grounding going to the frame of a PV panel could be smaller than this one, depending on the size of the PV panel, of course. So good insight, Felisberto. Thank you.
Okay, thank you.
Yeah, I hope it's clear for everyone. So let's move ahead. Okay, as we were saying, the protection devices that we use in installation, we have the general circuit breaker that will be there to protect the whole installation against overcurrents and short circuits. So when a general circuit breaker trips, all the installation will be in outage. So you will have power off everywhere. And usually when the general circuit breaker trips, that means the whole of your load must have an over voltage, not over voltage, over current anyway. Maybe the current's going to each circuit, the sum of them is the one getting this general circuit breaker tripping. It happens sometimes, which is not normal, and a common mistake we can see in our installation is we see the general circuit breaker tripping because of a fault in a single circuit, which should not happen. When there's a fault in a single circuit, it should be the circuit breaker dedicated for that circuit tripping, not the general one. It mostly happens when there's a mismatch in the selectivity, when there's no selectivity ensured within the design. So it's very, very important to ensure selectivity when you make the design. When we say selectivity just means putting all your devices in an order and making sure that the most downstream device will always trip before the upstream device. And it's done due to the reactivity time, the rating, and the characteristics of the devices, which is something we always should pay attention to make sure this thing, to make sure the devices will not trip in a reverse order. So then we have the residual current circuit breaker, which is the device will protect the system against leakage of current. This one is there mostly for protection of people, because whenever we have a current leakage, that could easily ignite a fire in the installation, or it could mean someone is in direct or indirect contact with current somewhere, which could be very dangerous. So the residual current circuit breaker, which we usually call RCCB, is there to protect against this specific fault. And the miniature circuit breaker, which in terms of functionality, it does the same thing as the general circuit breaker. The only difference is that this one here will be put to a specified circuit, not to the whole installation, but it's basically the same. And then when we talk about cable cross-section, it's not a specific device, but it's to remind you people that when we are sizing and making an installation, we should pay attention in the cross-section of your cables, because this is something very, very important in the protection of your installation as well. So the bigger your cross-section, the more current it can handle. The smaller the cross-section, the less current it can handle. So this is why the cross-section should be in direct rapport with the circuit you want to feed and the amount of power you intend to feed in this circuit. And this cable cross-section, you should pay attention to the circuit breaker you're installing in a specified circuit, because the cable cross-section will tell you what is the maximum rating circuit breaker you should put. So if you have a cable with a specified cross-section, you know in this cross-section, I'm only allowed to pass that quantity of power, then my circuit breaker should be this rate. So here are the devices, miniature circuit breakers. Yes, please, there's a question. Unmute, just give us your name and go ahead with the question.
My name is Shahabuddin Amini from Balkh Project, Afghanistan.
Yeah.
Sorry, sir, I asked this question previously, and sorry that I'm asking once again this. About the selection of the cross-section of electrical cables. For a small cables, already a proper sizing is provided by MSF in lots turning I've seen. Like for 4 mm cable wire, for 6 mm wire. But in our projects, sometimes we need to have a proper calculation format, for selecting cable cross sections. It depends to the length of the cable. It depends for installation. It's underground or it's in cable tree. So there's lots of factors that it's affect for sizing of the cables. So if there is any formats or any more informations about the sizing of electrical cables, we will be happy to share with us, sir.
Thank you very much, Shawad. So there's no particular tool to allow you to introduce not in our logly. As I'm aware of, I will have a deeper look on it and maybe get you back. But as long as I'm aware, I don't think so. And yes, for more complex installations, it is always a good idea. You could put all factors because it can influence on the actually current flow, like the temperature, how you are laying the cable itself, the type of conduit where you are using to protect the cable. All these factors could influence on the carriage current. Now, this is why, but in our constraints, in what we define in the logly and in the tables we have, you already have enough safety margin. So it doesn't matter the scenario we are, it's not likely that we go over this safety margin, because if you go in deep details with all these factors, you will always have a section that would be less than what you will find in our diagrams if you go with very, very deep details. And these are factors that could vary a lot because the climate is never stable. It will depend also on the ambient temperature and everything. So this will give you specific factors that you can combine in the equation. And in order to know that, there is a formula. Maybe after the meeting, Shawad, you can just drop me a text and we will see some things about that. I can share with you some Excel sheets on that, but if you are designing an installation in MSF context, these tables we have here for you, that would be enough. That's largely enough for the systems we usually work for, and we have enough room, enough safety room to make sure the section cable will fit the need that we are working with. So I hope I answered your question, Shawad.
Thank you, sir. Thank you very much.
Yeah. Now, so here we have some circuit breakers for the protection of the installation. We have the miniature circuit breakers on the left and molded case circuit breakers on the right. Does anyone know the difference between these two types of circuit breakers? I mean, there are several differences among them, but can anyone mention one difference? Yes, please.
Sir, in here we have two types of circuit breakers. One is MCB, main rate circuit breaker, and one is MCCB circuit breakers. For large amperes, you're using MCCB circuit breakers, and for a small amperes, we are using MCB breakers. So most of times, as per MSF standards, we should always use 4-pole and 2-pole MCB breakers. We should protect also the neutral line. And also the type of circuit breakers should be all the time should be the type B. As per the MSF standard, it should be type B, the type of breakers.
Okay, thank you very much, Shawad. So, as he mentioned, this is one of the differences and the main difference between MCBs and MCCBs. The MCCBs can withstand with very, very big currents. They can make pass big currents without, let's say, getting damaged. While the MCBs, they withstand with slower currents. In a normal scenario, when you have currents from 0 to 100 amps, you can easily get an MCB. But when you go over 100 amps, commercially, it's very hard to find MCBs that can withstand over 100 amps. So this is where you start going to MCCBs, molded case circuit breakers, also called compact circuit breakers. So the current is one of the main differences. And for some MCBs, another difference is because they are flexible, so they can be set. The tripping current can be set. It's not a fixed value. While in one MCB you buy, it has a specific nominal current that will trip whenever this threshold is reached. With the MCB, you can actually set this threshold, like for some MCBs, you have this option to set what should be the nominal current, how many amps do you want it to be. Apart from that, because they are completely regulable, some more advanced MCCBs, you could even choose the tripping curve. You can make it work as C-type circuit breaker or B-type circuit breaker. And for the ones that are combined with RCCB, because some of them can be combined, you can also set the RCCB part, even the reactivity, how many times it should delay before tripping the circuit. So these are the main differences between an MCB and an MCCB. And MCCBs, as you can expect, they are more expensive than the MCBs. In a normal installation, where we have good big currents, the MCCBs usually installed as the main circuit breaker only. And then after the MCCB, you have MCBs all around. So here you have 3 poles MCBs, which are not advised. Yes, please.
Just I'm going to add one thing more, sir.
Sure.
Maybe if I'm right or not, I'm to make the corrections
Go ahead.
myself.
Yeah.
For some area we have large cable, and instead of MCB, we are going to use MCCB because of the cable size. Am I right or not? Because we can find also the small amp of the MCCB also.
Yeah. Yes, exactly. You're right. And this difference in the connection terminal diameter is related directly to the current. Because the MCBs are designed to carry big currents, they should be connected to bigger cables. Small cables won't carry big currents. So naturally, we expect them to have these bigger sections on there. Now, if you have a system where you are carrying small currents, but you are using bigger cables, maybe because it's a very long distance and you're trying to avoid voltage drop, then it's one of the scenarios where you might be restrained to use MCCBs because you will not be able to fit your cables to the MCB, even though you have small currents flowing there. And then there you will be interested in having one MCB and set it to a smaller current. They can have small currents, but not that small because their range, they have a defined range, and this defined range doesn't go till values like 6, 16, or 20 amps. They could be like from 100 to 150, from 80 to, I don't know, 200, depending on the specific model. But yes, they can also come in the below 100 without getting much lower. So yes, in one of the cases is that we use these MCBs because of the cross section of the cable we are connecting. Exactly. Okay. So as we said, any short circuit or overload could lead to fire in a system. So this is why when you say these MCBs protects the system, the whole system against short circuit and overload, indirectly they also protect people against fire because they prevent short circuit, which could lead to fire. And in most cases of electrical fire, they are due to any short circuit or overcurrent in the system. Now, after the MCBs and MCCBs, we have the residual current circuit breakers. So this one here, the RCCBs, they are meant to protect the circuit against leakage of current, which means when you have a system, a power system, you have your current that should flow all entire the circuit and do the same way, like from the phases through all the appliances and back to the neutral. This is how a normal scenario should happen. However, due to any factor, we could have some current leaking out of the circuit. And this leakage out of the circuit can also be the origin for some, let's say, undesired fallouts, like could be any fire, could be an electrical shock, and things like that. So this is why the RCCB protect the system against leakage of current, which means what they do actually, and basically, you have your cables going from the neutral and the line. And the RCCB will actually keep monitoring the current flowing from the line and the current flowing to the neutral. Whenever there's a difference, and this difference goes over the threshold, which is usually 30 milliamps or 300 milliamps in MSF context, then the RCCB will trip because he knows there's a leakage somewhere, it could be a danger. So it will trip. This is how the RCCBs, they work. So in our installations, we put 300 milliamps at the top, right after the main circuit breaker, and this is for the whole installation, the main board. And then in the terminal boards, to protect all the circuits, we put 30 milliamps. So the 30 milliamps to protect the people, because this is like a threshold. If anyone gets an electrical shock with 30 or more milliamps, it could be very dangerous for the person. This is why I have this threshold of 30 milliamps. And then we have 300 milliamps in the main RCCBs to protect the whole installation against fire, because any leakage of this latitude could easily ignite a fire, especially if it happens close to any material that could be easily inflammable. So these are the RCCB. I don't know if there is any question about the RCCBs. Here we have 2 poles RCCBs for one phase system, and 4 poles MCCBs for 3 phases system. So as we were saying, any leakage protection device, it will cut if there's a difference between the current in live and the neutral wires. And here we have the miniature circuit breaker. So this miniature circuit breaker here, as we were describing previously, it's intended to protect the circuit against overcurrent and short circuit, as we were saying previously. And then the cable cross section, as we explained before. So all the cables should be very properly sized, which means the cross section should be in accordance with the power you want to supply, and then the MCB should be sized according to your cross section. There are standard cross sections that you may find in the market and use in our installations. And for each cross section, there's a limit of rating, current rating for circuit breaker. So as you know, and as we were saying, the more is your cross section, the more power you can carry through this cable. The less is your cross section, the less power you will be able to carry. So because there's an internal resistance of the cables, which means all current going through the cable will generate heat because of the internal resistance. And this heat could easily lead to fire. This is why we need to put a limit on the maximum current it can carry, which we do with our circuit breakers. And then we have here, in this case here, I hope you had the chance to see this. We have this document, this minimum protection in the logly. Here we have the main circuit breaker, where you have the power coming in. You have the RCCB after the circuit breaker. And one common mistake that we usually find in multiple installations is having the RCCB upstream the MCB. So many times we will find the RCCB first, and then the MCB here, and then from the main MCB, all the other devices, which is not the right way of doing things, because in the installation you have this MCB here is the one protecting the RCCB, not the opposite. So you should always put the RCCB downstream the MCB. And then you have the entire circuit, all the sockets and everything. And the sockets are connecting here to the circuits. So in a typical MSF installation, we use 10 amp circuit breakers to feed lights and 16 amp circuit breakers to feed sockets. So every installation will have at least these elements here. The MCB, the RCCB, one circuit of 10 amps and one circuit of 16 amps for the sockets and for the lights. Now, depending on the size of your installation, the number of appliances you will have in your installation, the number of sockets and of lights, you might have more circuit breakers of 10 and 16. You might have more circuit breakers of 16 for sockets and more circuit breakers of 10 amps for lights, depending on the number of terminal elements you have in your circuit, so the size of your installation. You could also have 32 amp circuit breaker or 20 amp circuit breaker if you have special circuits to feed big machines with high currents that cannot fit in 16 amps. Usually for this case, we can use like a 10 amp circuit breaker and send this circuit specifically for that particular appliance. One also common mistake we find in the ground is seeing people putting 20 amps or 25, even 32 amps to feed their ACs, split air conditioners. I mean, for most of ACs, they have smaller currents. I mean, an AC of 9 BTUs, 12 kilo BTUs, it will never be more than 16 amps. But a common mistake we find in the field is putting these bigger circuit breakers for ACs when we don't need them. So they can easily fit in 16 amp circuit breaker. So we can put them. We just don't put it together with other sockets. We create a dedicated circuit for the ACs and we can put 16 amps unless there are multiple ACs in the same circuit. There you should put a bigger circuit breaker, but it's always better to have one single circuit for each unit of air conditioner. So, and here the rating of this main circuit breaker will depend on the size of your installation. So after you have the power balance of your installation, you know the total power of your installation. This is what will dictate you the rating of this main circuit breaker here. And then the rating of this main circuit breaker will dictate what should be the power capacity of this RCCB. It should always be whether equal or bigger than the rating current of this one. So the rating current of the RCCB, of this RCCB here. So is there any questions about this minimum protection single phase distribution board? Okay, good. Then we move forward. One also thing to take into consideration is the cross section of this cabling here. You know, the cable that we use to make the connections between all circuit breakers. Usually, the cross section, the minimum cross section you should use to do these bridges here is you will get it from the rating of this circuit breaker. So which means if it's a 32 amp circuit breaker, you should not use a cable of cross section less than 6 milliamps, as you can see in the table here. You know, if this general circuit breaker is 20 amps, then this cabling here you use to wire the board should not be less than 4 milliamps. You could use 4 or more. And if it's 40, from 40 you should use 10 milliamps and so on. 10 square millimeters cross-section cable to wire your internal board. Now here's a three-phase distribution board. The principle is almost the same as the previous we saw for single-phase distribution board. The main difference here is just the main protective devices, the main MCB and the RCCB, which will be protecting all the circuits. So in the previous one, we have 2 poles MCB and 2 poles RCCB. So all the devices are 2 poles. While here in our 3 phases, the main MCB and the RCCB, there are 4 poles now, which means your cable providing circuit is a 3-phase cable. You have a 3-phase system, so all of them will pass through the MCB and the RCCB. From the RCCB, now you have 2 cable protection devices. So for each one of these single-phase protection devices, you can choose in between any of the 3 phases here and also put the neutral. And this choice should be done carefully in order to establish a balance between phases. If you overload one phase more than the others, you might have problems later, especially if you're using a power generator. Your power generator will not work smoothly as it should. So this is why you should make a good repartition of the circuits among the 3 phases in your main board and your distribution boards. So we move ahead to another protection device, which is the SPDs, the surge protection device. As the name says, this device will protect your installation from surges. So it will protect your appliances, your equipment, and the electrical installation itself from getting higher currents that can come from peak surges. So for very large surges, this device will trip and the cartridge will go up. You have to replace the cartridge when you have a lightning and the device does its work properly. And this is also in direct relation with your grounding system. So this is why it's always, your installation should always have a proper grounding system, because this device here will not work if your grounding system is faulty. So because what it does is actually take all the surge or all the spike that might infiltrate in your installation and then divert it to the ground. So it will use the grounding system to conduct your overcurrents or your surges to the ground. And these cartridges are replaceable, just like fuses. So in all the installations, it's always a good idea to have some cartridges as spare, because during maintenance and whenever there is a surge and one of the cartridges is out, you should always have this one here easily reachable to replace in your SPDs. And here's how we install the SPD in the system. This is the previous minimum protection single line diagram we saw, and this is how we should install the SPD. So after the main circuit board, we put the SPD. It should be downstream the main circuit breaker. One common mistake we see in the ground is seeing this SPD here upstream the main circuit breaker, which the best approach is to put it downstream the main circuit breaker. However, upstream all the other circuit breakers. And then you connect its grounding terminal to the grounding collector of your board, so it have a safe path to the ground. And then we talk about protecting sensitive equipment. I think it's something we mentioned before, but can someone recall us why do we protect sensitive equipment? We protect sensitive equipment from what exactly? Yes. Your mic is off.
Sorry, sir.
Yeah.
We are protecting all electrical equipment because of electrical fluctuations to keep our equipment safe and operation. In my point of view, that's all for keeping safe our device. We should protect because the great power, it has always fluctuations, and also all these safety things that you mentioned, it's for this that we should protect our device and ourselves, and we keep the project, the operation running.
Exactly. Perfectly. Thank you. So when we say electrical fluctuation, what we actually mean is voltage fluctuation, because yes, voltage is an electrical parameter, and this is actually the parameter that can fluctuate the most in an installation system, simply because it's generated by the source, and the source can sometimes is not steady as it should be or as we expect. So we protect from voltage fluctuations. We also protect it from surges, spikes, as we talked a few minutes ago about the SPDs. So we also protect against any surges. So here are the devices that we use to protect the equipment as we as we have mentioned them. We have the voltage limiters that will cut the power whenever there is a fluctuation in the voltage that could be harmful for the devices. We have the voltage regulator that will simply keep the voltage inside the range, so it will transform your voltage and keep it steady. And then we have the UPSs that will do the same thing as the AVR does. It will keep your voltage steady, will keep your frequency steady, and will give you some autonomy. And the UPSs are much more stable than the AVR. So they give a much cleaner energy because of the technology they use to perform this task. So as we say here, so these are some reference values and ranges. So usually voltage limiters can be at this range, which means it could support from, yes, there's a question. Just unmute, Shawad.
You hear me,
Yes,
sir, right now?
yes, we do.
I make a correction on myself for myself, sir. Am I right on or not? Some protective device itself need protection or not, like UPS. It's it has lots of cost. It's high. I mean the price is too high. We should protect also the UPS from against of voltage fluctuations. Am I right? We should before connecting the grid power to the or generator power to the UPS, we should install voltage regulator or not, sir?
Okay, thank you for this question, Shawad. So as we were mentioning, the UPSs and especially the Delta Employ UPSs we use in our projects, they already have the function of protecting your devices against voltage fluctuations. And the AVR you will put to protect the UPS, it cannot do this protection better than the UPS does. So the UPS was this protection, it was a range that it will always transform the voltage and give a better output on the voltage. However, if you are putting this AVR from the upstream, the UPS, it will not, I mean, there's no there's no inconvenient in putting, but I would rather use this AVR to protect other equipment that might need this protection more than protecting the UPS that has already this function. However, there are other things that you might want to protect your UPS from, like surges, for example. It's always a good idea to protect your UPS against surges. So this is why you should always have one SPD upstream and protecting your UPS. So we assume there is an SPD in the main board and the UPS is not far from the board, more than 10 meters. Then this SPD is also protecting the UPS. On the other hand, if the UPS is very far away from your board, then you should install another surge protection device, another SPD, near your UPS to protect the UPS against surge devices, because it's common to happen and to see one UPS getting damaged by the surges and the strikes. So yeah, this is where you need a protection for another protective element. It's always a good idea to have an SPD to protect these devices here. Even the AVRs should be protected with an SPD. Then I was talking about the range of volts for a voltage limiter, for example. They usually have 185 to 260. This range can also vary depending on the specific model and the brand of voltage limiter you are using. And for some of them, in this range here, you cannot like modify the range. There might be more advanced brands or specifications that you could change it, but for most of them you can't. So you have a range that could be narrow enough to protect your devices and keep your devices running. So this is it. Even for voltage stabilizers as well, there are ranges, defined ranges that it can, like if the voltage is in this range, the AVR will be able to convert this power and make the voltage stable. But if your voltage goes off this range, then the AVR is no more able to convert the power. What it will do is cutting the power. Because in this case, the fluctuations are so bad that even the AVR is not able to stabilize it. So it will cut until the voltage comes again to this window, and it will make the voltage stable to 30 amps and give you power and close the circuit again. So from the UPSs, as we were saying, their energy is very clean because the output of the voltage is not really conditioned by the input you have, as it's going for a double conversion process. So there is a very, very small impact for the output coming from the input. This is why they have a very, very clean power. And the batteries will give you more autonomy. Here, for example, usually you have the UPS and the battery pack with the Delta Amplon UPSs to provide you some backup autonomy. Now, one common mistake we usually see in the ground is seeing the UPS or using the UPS as a backup source for long periods. The UPS are not meant to provide the continuous power for a long time of outage. Their main use is to provide you some power while you switch from one generator to another, considering you have two generators in your setup. It's not meant to replace, for example, your generator, your main source, if this main source was let's say a pain that's taking long, because they have a short autonomy. The autonomy is not big as if you are using, like if you use an inverter with a proper battery pack. There you can use it as a proper backup. So the UPS is more there to use when you switch from generators, or when you have, let's say, a pain with one generator. The time you switch from this one to the second one, the UPS will ensure you power and will allow the power to be continuous for the loads connected to that. So these loads will not feel this change or this interruption in the power supply. So as I was saying, these devices here, they do not protect against lightning strikes. This is why we always need SPDs to protect them. Then let's talk about electrical safety. So in electrical safety, we mostly, yes, please.
Sorry, sir, I'm asking lots of questions because I'm electrician here in the Mazar project. So we are facing with lots of challenges here. I'm going to know what the question that I have. Sir, for the laboratory, we have for selecting the protecting device, like voltage limiter we have. Could we have something to know exactly where we can use the voltage limiters and which devices we can use the regulators? And sometimes we are confusing. Like already I have like 10 AC units, I can provide one voltage regulator for all of them, or I should provide a voltage limiter for each of them. So in some area, we are confusing for selecting the protecting device. So if you have some list that mention exactly what voltage limiters, which device could be you need protect, and which voltage regulators, which device could be protect, and also with UPS and which device. So it's my question.
Okay, thank you, Shawak. So this actually can vary a lot depending on the specific context, depending on the situation where you find yourself. For instance, let's say in a perfect scenario, UPSs would work everywhere. But as you know, UPS are very expensive. They are the better solution, but also very expensive. And we need to prioritize things. This is why we only use UPSs in very sensitive equipment like biomed and telecom. We can use these UPSs. And now for the equipment, let's say, for instance, a laptop, for example, even though they need protection against voltage fluctuations, they already have an internal battery. So you have some autonomy in there, which makes them a good candidate for voltage limiters. Whenever your voltage is not suitable, you could just cut the power and the laptop is still working. And when it gets better, you have the power back. So for appliances like this, you can just use a voltage limiter and you should be good. Now, for most of the devices and for all the devices that use a compressor, I'm talking about fridges, freezers, air conditioner, as you say, and this kind of things, it's better to use an AVR. The AVR would be a very good option because if you put an UPS there, you know, this material with compressors, they use a lot of power. So if you intend to put UPSs there, bear in mind you will have to buy big UPSs with big bunch of batteries that most likely you don't want that. So you put an AVR. And also because you'll avoid voltage limiters to all these kinds, because the voltage limiter will make a lot of stops and then starts again, you know. So it's always a good idea to use an AVR. And then for the other devices, more sensitive, as I explained, a UPS should do. As long as if power continuity is not something you really need for this scenario, you go for the EVR. Unless also continuity is something essential and critical for this specific scenario, then you go for the UPS, as we do for the sensitive material. So then
Got
here,
it. Thank you, sir.
yeah, you're welcome. So here we have this electrical safety thing. So when we talk about electrical safety, we are mainly talking about protection of your installation, protection of people, especially people, when we say about electrical safety. So here are the risks that we can incur in our installations: risk of electrocution and risk of fire if they are not properly protected. Can someone remind very quick what could be in the origin of an electrocution or in the origin of a fire in an electrical installation? What could be the cause of a fire or of an electrocution?
The rest you can also participate.
Anyone else? Yeah. Yes, there is Edgar.
Sir, electricity have two biggest risk. One is electrocutions, as you mentioned, and one is fire. And what is the cause of electrocutions? There is two main things. One is we have to touch with electricity, direct and indirect. Direct means when we are touching with some open wires, open junction boxes you are touching. And indirect means sometimes some electrical device like refrigerators, the cover is metal, and if the phase wire touch to the metal cover, we doesn't know that the cover is already connected with the phase. It means it's indirectly it has power. So if somebody touch on that, electrocution will be they got electrocutions. So for protecting the electrocutions, for touching the case of metal things, we have grounding system for safety measurement, and also for touching the open wires directly to the electricity. We have RCD breakers, as you mentioned previously. And also for the fires, if we not select the proper size of the MCB breakers and also MCC breakers and also cross section of the wires, so the fire will be happen. So due to this, for preventing the fires, we need to do proper cross sections for electrical cables and wires, and also proper sizing of our breakers, and also selection of the type of the breakers. So I think that's all from my side.
Thank you, Shawad. I think Edgar also had something to say. Let's go through it very quick, and then we move ahead. Edgar?
No, sorry, I don't have anything to say.
Okay, I thought I've seen your hand previously. Okay. So here, from electrocution, as he mentioned before, the electrocution can be due to direct contact or indirect contact with electricity. So direct contact simply means the person touches the cable, the conductor, directly, the conductor carrying electricity. Which indirect contact means the person touches a metal case, any plate that is also being touched by a conductor. And in both cases, the person will have a shock hazard. So this is the risk of electrocution. And then the risk of fire. The fire could appear in your circuit due to a short circuit. So when you have a contact between neutral and phase in your circuit, that's a short circuit, and it generates sparks and could very easily lead to a fire. Overload also can lead to a fire, because who talks about overload says overcurrent. When you have too many equipments connected to a single circuit that was not intended to feed all this equipment, then you are overloading your circuit. You have overcurrent. Overcurrent will heat up your cable, and your cable heated could generate fire. Low quality materials also could lead to fire. If you have material that, because of its low quality, at some specific point, it will not withstand with the current that is being supplied, it could also burn and then generate fire. Bad design, bad implementation of your system, it could also generate fire, because who says bad design would mean not designing the proper cross-section of the cable, not putting the proper protecting material. So if your system is designed in that way, there's a big chance you may have fire. And lack of maintenance as well, because it's always good to provide maintenance in the system. Always check for the connections, make sure they are very well tight, because some of the connections can become loosened with the time. And if they are not, again, make tight from time to time, when your connection becomes loose, it generates sparks, which could easily lead to fire. Then, in order to avoid this risk of electrocution, to minimize at least, you should install a proper earthing system. because the earthing system will protect you against indirect contact. So whenever there's a live wire touching a case and you touch the case, instead of having current flowing through your body, the current will flow through the grounding system to the ground, because a person will always have bigger resistance than the grounding system, and this is why the current will choose the path to the grounding system instead of the person. You should also have good quality RCCBs. We find very often in our projects bad quality RCCBs, which can be dangerous because these RCCBs does not give their protection properly. Some of them doesn't really protect them, depending on the brand and everything. So good quality RCCBs are always better. There are known brands that we should use and stick to them. Also, good quality protection devices and good quality MCBs to always strip whenever there is overheating of a cable. The MCB will trip before some fire starts. So it's always, we should always have good quality MCBs. Good quality equipment and terminals. So that comes to the connection thing. So you do very tight connections using good quality material, like Wagwas, for example. And we should always use junction boxes because it will prevent then your connections from having contact with other external element or from sparks to go to have contact with other elements. The cable should be properly fixed in the wall. The cable and all the elements like sockets, switches, and everything should be very properly fixed and attached to the wall. And always use qualified technicians that can ensure all these instructions are followed up and can ensure our guidelines are followed. So, is there any question? So, if not, we will move to the study case. I don't know if anyone has tried to do the study case. I hope most of you done. For those who did not yet did the study case, it's not too late. We will now work together on it, and we will try to go a bit quick on it as we don't have much time left, and see key aspects. If anyone has a particular question on the sizing, on what he was trying to do, you can sorry, I was muted. So I was saying that we will now go to the study case that Caleb left in the last session. There was a study case. So did anyone try to do the study case?
You mean, sir, previously the LTT training and
Middle session.
yes, we completed that one. I completed all the parts previously.
Perfect. So we will go together through it. Shawad, there is someone with the hand, Biomed Tech. Please go ahead. You're on mute.
Yes.
Okay.
No. Okay. Yes. I didn't finish the case study, but in the I think that in online modules, I just I missing only the case study, and I have some
Okay.
questions about the case study. First is after about the some devices, some powers. For example, for ventilator, outlight bulbs, and light bulbs. I put this, but I didn't put the location. Yes, of
Yes.
these devices. It's not affect the final power. No.
No, the locations of the device where the device is does not affect your final result. The
Yes,
location will simply help you have, let's say, a visual mind of where your things are. So in case you need to create a specific circuit to a specific piece, you have an overview of which devices are there, so which power you should put to this circuit. But it does not have any impact on the overall result for your generator sizing.
Okay. The second question is about a primary electricity source. Yes. We can have. This is a question. We can have a generator has a primary electricity source in some cases.
Yes.
Okay.
Actually, this is the scenario in most cases. In most of our projects where there's no city power, most of the time we will be using generator as the primary source. And then as the secondary source, you could have another generator or backup if you don't have much loads to feed. Just like a backup batteries or another generator to do the changeover with the primary one.
For other equipment, we didn't have here the power, but I go in the Unicat and I find there some models and I take there the powers, some values, and I fill here. This is not problem.
Perfect.
No.
No, not at all.
But
this is actually the approach.
Yes.
I mean, here in this case, we go through Unicad and we find it because we have it available. Supposing you are in the field, then you don't go to Unicad. If you're in the field and it's a real scenario, then you have the device there. So if the device is there, you just go there, you read the plate, and then you have the most accurate value.
Okay. Thank you. And other question is about a list of material to order from MSF Logistic. In this case, I don't know. We have to think about all things we need to make installation. We are talking about properly generator, cables.
You need your source.
Yes.
Exactly. So, because you are setting up an electrical system, it's a power distribution system. And as we said, in the 4 components of the power distribution system, everything you have there in the scenario already is the appliances, the equipment that they listed. Now, the distribution, the cables and everything, the protection system, the power source, all of these you should provide a list of material that you will need to acquire in order to set up this electrical system for the hospital.
Okay.
So I will open here so you guys can have a comparison and go together. I'm sharing again my screen. Okay. Now I hope you can see my screen. Everyone can see my screen. I'm gonna zoom a bit more so it can be more clear. Okay, that's okay, perfect. If the numbers are perfectly visible to you, good. So In the case study, this is our hospital that we need to electrify, see the needs and everything. So here's the list of equipments, and then here's what we are expected to do. Define the power strategy for the health center. Primary electricity source, backup electricity option. So here in the power strategy, because there is no city power, at least it was not been mentioned here at the context. So we assume there's no city power in this specific context. So we are going to use a generator.
Yes.
We use a generator among all the power sources that we have mentioned before. The grid is not an option. We don't have it. The generator is a fast option. We could go, let's say, for a solar system, for example. Solar is something that will take you more time, and it needs very, very experienced people. So we go for solar system in case there is, for example, any problem with the fuel, with supplying the project with fuel or things like this. Or if you have enough time and you know we can put a proper solar system before the time we expect to begin the activities and we have the proper budget. In this case, we will also prioritize the solar. Now, here, let's define 2 power generators as our strategy. We need 2 power generators because we need the main source and then the backup source. So one generator as the main source and the second generator as the backup source. So both generator will switch together, one and the other. So here, did anyone choose another, let's say, another power strategy that are not power generators? Okay, then we are all aligned. So once we have chosen the power generators, now we need to size our power generator. We need to know how big should our generator be, how many kVA. So here we make the list of all the equipment, as the equipments are listed here. So we just take all this list of equipment and we put in the sizing tool. I hope everyone could access the sizing tool. It's in the in the course itself and also in the logly. You can easily find it in the logly. If anyone has issues finding the tool, just drop me a text in the message and we will go together through the folders to have the file. So here we have the file and here is where we do the sizing. So at the end as input, we put all the appliances, the number, the power they use, how many hours per day they are being used, and the type of appliance they are. So we fill in the blank spaces. We fill in the blank spaces, and then as the output, we will have the consumption and and from this consumption, we must know what size of generator we can use. So we have filled here the power, the percentage of use, and the type. So all this data here is already provided in the file. So in the field, you should know which appliances you have and for how many hours each appliance is going to run. So these are all this data we fill here. Then here, according to the appliance type, we must be able to say if it's a motor, if it's a resistance, or if it's a compressor. This is just a matter of knowing the kind of equipment. Like for every equipment with a rotative component, it should be a motor. Like fans, they are motors. If you have any fans in your thing, vortex mixer, you know, the mixer itself is a motor. The ventilators are motors. The water pump as well. There is a motor in your water pump. So for these devices, we put motor here. For devices that work as a with thermal things like air conditioners, fridges and freezers, they are compressors. So here we should compressors. These are thermal equipment. And then for the others like lighting, most electronic equipment, there will be resistance only. So it's important to fill in correctly these things here because they will give you a power factor. Depending on the type of appliance, you have a power factor and you have a starting coefficient. So you should always fill correctly this thing. Once you have all this done, so all these other cells will automatically fill. And then you have the total here. So here, let me move a little bit this thing here. So here you have the power factor, which will automatically be filled once you have the type. Then you have the power in volt amps. This and this power here is just the product of these two. After the power, here you have the max power. And then here you have the real power. And this real power is a calculation made considering also the percentage of use. And then we have here the real power. And the sum of this real power gives us this here. So the total consumption of our system, considering all the loads we had there, is something nearly 4 kVA. Did everyone, for those who did the exercise, did all of you guys had this number here or anything close to this? Perfect. Then we are aligned. So you have 3.9, and then we always include a 20% of safe margin, because what you are doing, this calculus might not always be exact. So we put this margin also in case we have some appliances that might be added in the long term. So we put a 20% safety margin, then it becomes 4.7. And for this 4.7, this is where you choose your generator. Now, when choosing the generator, the power generator, we never choose exactly power we have here. If we choose a 4.7 kVA generator, it will run at very full capacity, which can be harmful for the generator. The generator will run more smooth when it is around 60 and 80%. Between 60 and 80% is the beta load ratio for your generator. It can even run lower, up to 30%, even though it's not the optimum range, but let's say it will not be so harmful as if we were below 30 or above 80%. Yes, please. Raise one hand. Just unmute. You're on mute.
Yes, I said for me, I have something near, but because I didn't use a water pump with 2000 watts, I have something like a 1000 half.
Okay. Yeah, you're
Yes,
talking about
and
water heat, I think.
yes, and
Yes.
here the coffee maker I didn't find of 1000 half, but I found of 65 605. Then is the reason why I
605
think that
only. Okay.
yes, is the reason why I think
Yeah.
that the totally result is not
So
exactly the
yours
same.
is
Yes,
slightly slower, right? How much did you have
I have
exactly?
here 3.8 totally
Okay.
kVAs.
Okay.
3.8, yes.
Okay. Okay.
Yes.
3.8. It's close enough. It's close
Yes.
enough. Especially because the coffee maker won't make a big difference, because you see the percentage here, it's 0.2%, because it
Yes,
only
yes.
works for 2.5 minutes. So the impact
Yes, yes.
is very, very, very slow,
Okay.
very
Okay.
low.
Okay. Thank you.
So then, and even with this small difference, when you make the safety margin and you choose your generator, because the generators have standard sizes, most likely we might fall in the same generator, the exact same generator. We might come up to the same generator. So Let's move ahead then. After I have this, we choose the generator. If you have 4.5, let's see here, let's fill here with some to see which generator will better fit in the load we have. So I have 6.8 here, which was what I choose, but the approach is, I will first take it out. If you have 4.5 and you put here 4.7, you see, this is exactly what we have, and you are loading your generator at 100%, which is not a good approach. So if we go, let's say for 10, then our generator is at 47%. It could work, but it's not either a good idea because there we are not at the optimal power that we need. And also because you have a variable load profile, there will be times, if you go with this power, there will be some times when the load profile is low, where your generator will be running almost empty. And on those specific times, you'll be killing your generator. You will be shortening the lifespan of the generator. So this is why it's not even a good idea to start with in this approach. And it is something we see in the field many of the times, and we see a very big generator for a load profile that is very low for the generator. So if we go for this, we have 68%, it's much better. But then if I go for, let's say, 7 or 8, here we are something good. But the best is to do this exercise with a catalog. So you don't choose you see, if you have a catalog, you could go for a catalog of any good non-brand. That could be FG Wilson, SDMO, Caterpillar, let's say the available brand in the context where you are. Available and good brand, of course. So here, if you see the first one is 6.8, the prime power. So with this 6.8 prime power here, if we fill here 6.8, we are near 70%. And this is a very good spot to choose your generator. Here you have a very good power. You are loading your generator in a very smooth power. Your generator will run smoothly. So this is a good spot to choose your generator. We take this FG Wilson and then we just fill in with the characteristics of the generator. So the nominal power is 6.8. In the max power, we put this standby power, which is 7.5 that we have here. And then the max intensity will be 11. Does someone knows why 11? Because we just put it's 11, so the 11 amps here, we have 6,000.8 divided by the voltage, which is 230. It's actually 32, not 11. 11 was for another power generator. So this power here divided by the voltage of the generator, you have the current, which is 32 amps, the output current of the generator. Now, we should choose a generator of a single phase because we have less than 12 kVA, and when we were talking about power sources, whenever I have less than 12 kVA, it's always preferable to go for a single phase generator. Otherwise, it won't be enough power per phase. So this is a single phase generator, and always, whenever you can, choose 1,500 RPM type generator instead of 3,000 RPM because they are more solid, more stable. They have a bigger lifespan, and their power are cleaner than the 300 RPM generators, and they are not noisy. So here we have our generator sized, and the result is this 69% of our power generator. Now that we know which power generator we are going to install, we know it's single phase and 1500 RPMs. This is actually the model. The model of the generator here, FG Wilson P751S. This is the one we've choose here. Then we have the most important thing done for our scenario. So here we could set our generator, which will be this one here. Let's go, which will be the PD initial quick place there. So here we have our power generator, which will be here at that spot here. So we set all the needs, all these appliances, we set the power generator. Now, what we are still missing is to do all the rest. A design for the generator shelter. Here, I don't know if you guys had time to go over the document. There is a document about the design of the power generators, the minimum requirements that you should meet when proposing a design for your power generator. So this FJ Wilson generator has already this case to protect the generator against rain and this kind of things. However, you could do the gen filter with these fences here, as in the document. Anyways, whenever you can, it's always a good idea. It can also be a good idea to do a proper house with a wall and everything. But as long as you have enough space for circulation, so your generator doesn't heat up a lot. There are also constraints on the spaces you should leave between the generator and the walls. And then you should always have this pipe here for the exhaust of the generator. So all the smoke and the things of the generator, the exhaustion will go out of your house. And after this, you have the design of your house. You should do the last a list of the items that you will need to put in place your thing. This is like a bill of quantities we are going to have here. So let's go through the main components that we can use here. First of all, once you're installing the generator, what do we need here to make this installation happen? And all these items you can find in Unicat. They are all listed in Unicat. So if you have the generator, that means you will need a distribution board, a board here near your generator. So it's always a good idea to have in your board. You will have an MCB, and this MCB should be 32 amps, as we have seen here. Our generator is 32 amps. So you will need to put an MCB 32 amps here. And this generator is single pole, so it will be an MCB 32 amps 2 poles. But of course, you get the description from Unicat with the appropriate code. You know, if you have the MCB, you will need a cable to transfer the power of your generator. And usually, because it's a single phase generator, the cable is 3 conductors. So who knows the cross section we should use, considering the generator is 32 amps? So the cross section should be minimum 6 milliamps. Depending on the length of your circuit, it could be more than 6 milliamps, than 6 millimeters, to avoid voltage drops. So it could be 6 or 10 if the distance is a bit long. Yes, go ahead. There's one hand up and you are muted, Shara. You are muted.
No any questions, sir. Just you
Yeah.
asked about the size of the cable cross section.
Exactly.
Yes, I'm agree with you. 6 mm or 10 mm. It's as per the
Exactly.
we have 32 amp. Yes, load. It will
Exactly.
be. Yes, thank you.
Yes, that's the thing. That's exactly the thing. So, amps. So This is the cable, and the quantity will be the distance between your generator and your main board. So you will always need a manual transfer switch. A manual transfer switch is always needed. So their specific rating for manual transfer switch, here we have 32 amps. So something like 33 amps for the manual transfer switch would do, but you could go even up. I mean, going for an upper manual transfer switch is never a bad idea. So you could have 163 amps manual transfer switch to switch between generators, because you have two generators, the second generator being a backup. And then you have MCBs, this first MCB is here. So the surge protective device, you will need one type 1 for the main distribution board, and then you will need surge protective device type 2 for other distribution boards, for the terminal distribution board. Apart from this one, you will need other circuit breakers. We will need our CCB 300 milliamps to protect the whole installation against leakage. And this one, the main breaker is 32. So this one should be 40 amps because there's no 32 amps RCCB. Then you will need other RCCBs with 30 milliamps for the terminal boards, for the secondary boards after the main board. And these small ones here, the quantity of them is the quantity of boards. Considering our installation, considering our scenario here, we might need something like, it's a small hospital, maybe something like two boards would be enough. So if you add you see, it's a small hospital. There's not a lot of, the installation is quite small, so you could put one circuit breaker to feed one side, one hole, and one one board to feed one hole, and one board to feed the other hole. So like two boards would be enough, and that would mean here going for also two RCCBs of 30 milliamps. And then you go for the MCBs. All the MCBs should be there for all the circuits and everything. So I let you guys complete the list with the MCBs that we will need for each board and everything. I don't know if there's a particular question on this case study. So you will need MCBs also for the rest of you will need more cable for your circuits, which are cable of 2.5 and also cables of 1.5 square millimeters. So all of this you'll need in your bill of quantities. Then you go with the quantities here and the codes, the Unicode codes of all these items you will find in Unicode. So I think that was all from the study case. If there's any question.
There's a comment on the chat from Noel, and he's showing us a board that is in Unicad, and if he's asking if we can use these kind of boards.
Let's see. So the image is not very clear. Yeah, I see. So this board here, Noel, actually, this board here can be used in emergency situations. You know, when you have, let's say you are in a scenario where you need to set up an installation, like you are mounting trigranos and everything, most likely you will be in a rush, especially in emergency projects. You'll be in a rush and maybe you don't have time to make a proper design before starting the activities. So these boards here are must for this kind of cases, or when you are running, let's say, a mobile clinic and you need power where you are moving for, because it's an all set board with its devices built in. It's not really sized for what we need. So you should not consider it in a longer term for proper installation. Even though we use, it's a material that we can use for specific emergency cases or mobile situations. I don't know if I could answer your question, Noel.
Yes, apparently he said that it's
Yeah.
okay.
Okay, perfect. So we're almost at 2 p.m. I don't know if there's any comment before we leave. Any other input?
So remember that this session is being recorded, so the video will be available on the Tembo course. So for the ones that has not done the case study or has any question related to the final modules and you did not complete it yet, so you can go through the video. And this will help you also to do the case study. And to complete, the idea is for you to play a bit with the tools. This exercise, I mean, the idea was for you to think a bit on the needs and use the tools for the calculations. Yeah, Dimitrio, go ahead.
Hello. Yes, hello guys. My name is Dmitry. Yeah, I'm from Ukraine, logistics manager. Just one question. Yeah, if I have some questions during this case study training, may I ask in the chat or?
Yeah.
I mean, some technical
In
maybe
the
issues.
in the forum, in the forum in Tembo, have. I mean, you say that you did not have access into the Tembo course, but if you want to stay at the end of the session, I can also show you how to do it. But if you enter in the Tembo course of LTT Energy, then at the first part of the course, there is a place that say forum. And in that forum, you can ask, you can put your questions, and then we will answer. If not, send me send
forum,
a message.
Yeah, I found. I already
You found the forum.
Yeah.
Okay.
Yeah,
So from
yeah.
there you can ask.
Yeah, I see you,
Yeah.
Noel, and you and some. Okay, yeah. Thank you very much.
From there you can ask, no problem.
You're
So
welcome,
this forum is open for all of you, like at the end, until the end of the course, no? So you can ask questions in this forum, and then Aurelio or me, depends on your question, will answer. But then you need to know that the course, it remains open for you as a consultation, so you can use this course as a tool. You have access to the course even after the end of this month, so use it during any time, whenever. All the information is there. The only thing is the forum. The forum, you can use it for the next, let's say, 2 weeks, and then we need to let free Aurelio and the rest of the team, so we cannot keep asking questions relating to the course. But the content is there. Use it if you need it.
Okay. Thank you very much, and thank you for the sessions. Yeah, it's very useful.
No
nice.
problem. Thank you.
Thank you,
Dimitri.
Dimitri.
Thank you very much. So take the next days to finalize the activities if you didn't do it yet. You still have some days to finalize the course. The recorded sessions are available for you in case you have any question, and yes, and use the forum for the next days to clarify any question you may have. I think that Stanislav is asking something in the forum. Let's see.
In the chat or in the forum?
In the chat, sorry. He's typing. While he's typing, okay, let me stop the recording session because I think that we are almost done.
Yeah.
So